This is B. Naresh, working as assistant professor in EC department. And today's topic is tunnel diode. So, in this session, we are going to discuss the construction of the tunnel diode and the operation of the tunnel diode, along with the VI characteristics of the tunnel diode, along with energy band diagrams. Then we will discuss what are the advantages and disadvantages of the tunnel diode. So before going to this tunnel diode, the tunnel diode is also one of the semiconductor device, and it is also made up with a P-type and N-type materials. But what is the difference between a normal PN junction diode as well as the tunnel diode? We will discuss here. So coming to this tunnel diode, if you consider, and this tunnel diode is made up with a P-type material as well as the N-type material. So let us consider, and we know that for a normal PN junction diode is made up with P-type material as well as the N-type material. And if you consider the P-type material, the majority charge carriers in P-type is holes. So means a trivalent impurities are doping with a normal semiconductor or a pure semiconductor is called as a P-type semiconductor. Whenever a pentavalent impurities are added to the a pure semiconductor, then it is called as the N-type extrinsic semiconductor. And based on this doping concentration, the majority charge carriers in this N-type materials are electrons. And for this case, so let us consider if in a P-type or a N-type, in a normal semiconductor, if you are doping with a semiconductor is a doped with half is a doped with P-type material, another half is a doped with N-type material. And in this case, in the P-type, we know that the majority charge carriers are holes. And in the N-type, the majority charge carriers are electrons. And when we are intersecting a P-type material and N-type material, that it is called as a PN junction. And due to this formation of the PN junction, it establishes a depletion region nearby the PN junction, and this is called as a space charge region, as well as it is also called as a depletion region, space charge region, or it is also called as the depletion region. Then if you want to allow the conduction across the PN junction diode, now we need to apply the biasing for this PN junction diode, means to absorb the flow of conduction across the PN junction, means how the charge carriers are diffusing from the one region to the another region to allow the conduction in a PN junction. So based on that, we have the two types of the biasing concepts, means the way of approaching the external electric field to an PN junction is called as the biasing. And how we are approaching the biasing to the PN junction is defined as the two ways. One is defined as in a forward direction, that is nothing but a forward bias configuration. Another one is under the reverse bias configuration, that is called as a reverse bias. So what happens? Already we discussed in a forward bias means whenever let us consider this is a normal PN junction diode, and this is a P-type material and N-type material. If a P is biased with the positive pole of the battery with respect to the cathode or N-type material, means N is biased with a negative pole of the battery and a P is biased with a positive pole of the battery, then we can say that this particular PN junction acts as a forward bias. And due to this, the approaching of this forward biased configuration, so we know that in a N side, the majority charge carriers are electrons, and the electron is a negative charge particle. And for this negative charge particle, and we are applying the negative force, hence due to this negative force, the electrons means, and it requires, so how much energy is required to broke this diffusion region or to cross this depletion layer or the space or region means, so we required a higher potential than this space charge region. So whenever we are applying the force to an electron, that force should be higher than the space charge region voltage. Then only the electrons are diffusing from the N region to the P region to pair with the majority charge carriers of the P type, that is the holes. And whenever this electron is paired with a hole, then it takes as a electron and a hole pair is a disappear. Then the conduction is takes place means the electron is moving like this. The current, conventional current, is flowing from the anode to the cathode. And similarly, we also observe that in reverse bias means when we consider a normal PN junction diode, and this is the P type and N type. Whenever the P is biasing with the negative pole of the battery with respect to the N type means N is a bias with the positive pole of the battery. At this point, the way of approaching this force to an PN junction, here it is called as this particular PN junction is acts as a reverse bias. Under this reverse bias, what happens? So let us consider if it is a normal PN junction. So, and this is the junction, and without any external biasing energy means if you are not applied any energy between the PN side, and this is normal depletion layer or a depletion width or a space charge region. And let's say this is the P type and N type. If a P is connected with the negative pole of the battery and N is connected with the positive pole of the battery, then we can say that this normal PN junction diode is acts as a reverse. Due to this, the way of approaching this external electric field to an PN junction, so what happens that in the N side, the majority charge carriers are electrons. So here it is represented as electron. And this electron is a negative charge particle means always the electrons are trying to attract with the positive energy. That is the reason. Electrons are not diffusing towards the internal region, but these electrons are diffusing or towards the positive pole of the battery. And similarly, if you consider in the P side, the majority charge carriers are holes, and due to an approaching of this electric field means a negative energy is biased with a P type ends, and here we know that electron is a positive charge particle ends. Holes are always trying to be paired with the negative energy. So hence, under this reverse bias, the majority charge carriers of the P type and the majority charge carriers of the N type is not diffusing towards the internal regions, but they are diffusing towards the battery. While this diffusion of the charge carriers of the P-type material and N-type material, it increases the depletion weight, means it leaves the space. It forms the depletion weight. And at this point, so you have the more space charge region between the P-type and the N-type ends. There is no movement of the charge carriers from the one region to the another region to pairing of electron and a hole pair ends. There is no conduction takes place across the PN junction diode under reverse bias. So this is the normal PN junction diode principle. Now we are going to utilize this principle to understand the tunnel diode principle. But actually, what is the tunnel diode? And so in this tunnel diode also, we are going to utilize the materials like P-type material and N-type material. So hence, this tunnel diode or it is also called as a Saki diode, is a thin junction diode. Means the depletion, the thin junction means here the depletion width is very narrow. The depletion width is, or space charge region width is very narrow, which exhibits again. And one more property is there in the tunnel diode, and it exhibits the negative resistance under the low forward bias condition. Means actually we have the two types of the characteristics. In a linear, either that is a positive resistance or a negative resistance characteristics. If we observe the positive resistance, means if the V is increases, the current is also increases proportionally in a linearly. Either the V is decreases proportionally, the current is also decreases. And this type of the characteristics of particular device is belongs to positive resistance characteristics. Suppose if a V is increases, I is decreases, or V is decreases, then I is increases. This type of the characteristics belongs to negative resistance device. So we will see in the characteristics of in a tunnel diode, how it satisfies this thin junction and how it exhibits this negative resistance under the forward bias conditions. But what is the difference between a normal PN junction diode as well as the tunnel diode? For this case, if we consider a ordinary PN junction diode, the impurity concentration, so that is about 1 part in 10 to the power of 8. So this is the doping concentration. So in a normal PN junction diode, that is 1 part in 10 to the power of 8. But if concentration is increased while I'm purifying the atoms in the level of 1 part in a 10 power 3. So in a normal semiconductor, the doping concentration or impurity concentration is 1 part in 10 power 8, but this is so 1 part in a 10 power 3. And this type of the doping concentration is involved to construct a tunnel diode here. So that is the reason this type of the diodes or belongs to tunnel diode. So this is the basic difference between a normal PN junction diode and so why? Because of that. So here also we are going to use in a tunnel diode also we are going to use P-type material and N-type material. But how we can differentiate how it is belongs to either a normal PN junction diode or when it is belongs to tunnel diode. So that is the reason. Based on the impurity concentration, we are classified as either it is belongs to a normal PN junction diode or a tunnel diode. So if we consider the normal PN junction diode, the doping or impurity concentration is 1 part in 10 to the power of 8. But if you consider the tunnel diode, the impurity concentration is 1 part in 10 power 3. Now, coming to here, so in this case, and why it satisfies the tunneling principle. So why it is called as the tunneling diode. So if you want to understand this principle, let us consider a normal PN diode, and I am going to consider a tunnel diode. And here I am going to take, this is a potential barrier when we are forming the intersection of, a P-type material and N-type material. And let us consider this is the height of the potential barrier. This is the height of the potential barrier. And this is the depletion width. Let us take this is the P side and the N side. And a normal PN junction diode. And we know that the N side, the majority charge carriers are electrons. So let us take these are the electrons are available in N side. Let us consider And in this case, if you are considering this normal PN junction diode, and this is the space charge region, if you want to diffuse the charge carrier from this one region to the another region, the condition should be the energy or the potential barrier of electron is always higher than this space charge region. Then only that electron is diffusing from the n side material to the p side material. So from that representation, so these are the a low L charge particular. Suppose if you are having this one, so yeah, there is no potential charge here. And so let us consider under this point, and up to this point, it contains some energy, and in this case, the electron has the lower potential compared with the space charge region. Hence, up to this point, none of the electron is not diffusing towards the p side to allow the conduction. But in this case, let us consider these type of electrons, and here there is no potential barrier. And let us consider the space means the electron charge energy or the potential barrier or the potential energy of this electron is higher than of this space charge region, then these electrons are easily diffusing from the n region to the p region to form the conduction or to allow the conduction in a p-n junction. So for this case, in a normal p-n junction diode, we know that the depletion width is very large compared with so means the width is a very large in a normal p-n junction diode, and it has some amount of space charge region or a potential barrier. Hence, if you want to diffuse the charge carriers from the region to the n region to the p region, then we need to have the higher potential charge carrier of for the electrons or holes compared with the space charge region. But coming to this tunnel diode, in a tunnel diode, and we increased the impurity concentration. So in this case, the impurity concentration we taken as 1 part in 10 to the power of 8. But in the case of tunnel diode, the impurity concentration we consider as 1 part in 10 to the power of 3. Hence, let us consider, and in a due to this impurity concentration, and it contains initially we told that the tunnel diode or Isaki diode is a thin junction, so that is the reason the depletion width is a very narrow compared with a normal p-n junction diode under the unbiased condition. Under the unbiased condition means we are not applying any external field or external force to a normal p-n junction diode or a tunnel diode, and due to the intersecting of this p-type material and n-type material, internally it forms the depletion width, and in a normal p-n junction diode, the depletion width is very large compared with the tunnel diode. Hence, this tunnel diode or Isaki diode is represented as a thin junction diode. Hence, so that is the reason. And let us consider this is the potential barrier and height of the potential barrier. And let us take this is the n side and this is the p side. And we know that due to this impurity concentration, the majority charge carriers in the n side, that is electrons. So let us consider this is the electrons, and now I consider. So, and the principle is the same. If you want to diffuse the charge carrier, the potential energy of the charge carrier must be higher than the space charge region. Under this condition, let us consider these are the charge carriers. Now we have the higher potential compared with the space charge region, hence it is easily diffusing from the n side to the p side to allow the conduction. But and due to this formation of the thin junction compared with a normal junction, and this is the, let us assume that So these are some of the electrons having the lower potential compared with the space or region. Even due to this, the formation of the thin junction, these are the charge carriers are also diffusing towards the opposite region to allow the conduction. But in the case of normal PN junction diode, these are the charge carriers. These are the charge carriers are not diffusing towards a P side region. Why? Because of these charge carriers having the lower potential energy compared with the space charge region. And why? Because of the depletion width is very large in a normal PN junction compared with a tunnel diode. But in this case, in a tunnel diode, we have the very thin PN junction. Hence, even though if the electron has a lower potential compared with this spatial region also, these are the electrons are trying to pair with a p side region of the majority charge carriers. Hence, it allow the conduct. And this type of the mechanism here, it is called as tunneling. This type of the mechanism here, it is called as the tunneling. Hence, this type of the diode is called as the tunnel diode. So this is the difference between or how it is conducting, why it is called like the tunnel diode here, and what is the mechanism of the tunneling mechanism. So based on this principle, now we are going to observe the working principle as well as the characteristics of the tunnel diode. So actually, if we consider the normal PN junction diode, we observe that one is unbiased PN diode, and similarly we observe that with respect to this is so without biasing, that is called as unbiased or zero voltage is passing through the PN junction diode. But now, with respect to the biasing, we have the two types. One is forward bias, another one is a reverse bias here. Now we'll see what happens forward and as well the reverse. Similarly, in a tunnel diode also, we have one is unbiased and another one is with respect to the biasing. And in the biasing, we'll see what happens if the forward voltage is increasing. So that is the reason. And that should be observed with respect to the energy band. To clear understanding of the tunneling principle, we need to understand with respect to the energy band diagram. And we know that what is the energy band diagram? The energy band diagram contains a P side region as well as the N side. In that we have the valency band and as well as the conduction band. And one more is a Fermi level. For a pure semiconductor or a intrinsic semiconductor, the Fermi level is always centered between the valency band and conduction band. Then based on the doping concentration, the Fermi level should be changes towards valency band or a conduction band. So hence, and we are going to observe the principle of this tunnel diode with respect to the energy band diagrams. So for this case, let us consider the working of tunnel diode with a unbiased condition. So what is the meaning of unbiased? So unbiased means we are not approaching any external electric field to this tunnel diode. That is nothing but a unbiased tunnel. So that is the reason. When a no voltage is applied to the tunnel diode, it's said to be unbiased tunnel diode. And for in this case, in this tunnel diode, the conduction band with the unbiased band. But if you take in normal PN junction diode, the Fermi level is always centered between the valency band as well as the conduction band. But in a tunnel diode, we observe that the doping of the impurity concentrations is very greatly increased. That is 1 part in 10 to the power of 3. Due to this increasing of the impurity concentrations in this tunnel diode, and this conduction band of the N-type material overlaps with the valency band of the P-type material. the region is due to the important region is the doping concentration is very large compared with the normal PN junction diode. So due to this heavily doped means 1 part in 10 power 3. Due to this doping concentration, the conduction band of the N-type material is overlaps with the valency band of the P-type. Hence, I'm going to show it. This is actually so that this let us consider this is the Fermi level. The dashed line indicates the Fermi level, and above the Fermi level we have the conduction band, and below the Fermi level we have the valency band. So means for if it is a normal PN junction diode, it shows like this. So means this is the Fermi level. So and this is P type and this is the N type, and this is the conduction band and this is the valency band. But if you observe, due to this large doping concentration is involved in the tunnel diode principle, so what we observed, the conduction band of the N-type material is overlaps with the valency band of the P-type region. So this point. So when you are heavily doping, the conduction band of the N-type material is overlaps with the valency band of the P-type. Hence, so this conduction band means this is a normal conduction, normal a PN junction diode. Due to this doping concentration, this conduction band should be increased. Means so like this. So this amount of charge carriers will be, so doping concentration means the conduction of charge carrier means conduction of the impurity concentration is also increases. That is the reason. This conduction band is overlaps with the valency band of the P-type region. Now these are the available charge carriers, freely available charge carriers to allow the conduction. Similarly, if you are taking the valency band due to this P-type, the valency band of the P-type is overlaps with the N-type. The overlaps with the N-type conduction band here. At this point, let us consider with the unbiased diode means. Let us take this is a symbolic. If I do the symbolic representation, this is the P side and N side, and we are not applying any external field to this PN junction. So what happens? And there is no movement of the charge carriers from the one region to the another region. So why? Because at least it requires a small amount of energy. But in a normal PN junction diode, it requires a potential barrier, means it requires some energy of that should be always higher than the space charge region. Then only the charge carriers are diffusing from the N type to the P type or a P type to the N type. But compared to this tunnel diode, it should be operated with a very low voltages, hence it requires very small amount of voltage. Due to the small amount of voltage, the charge carriers are trying to diffuse from the one region to the another region. But in this case, this is the tightly bound, means this is a valency band. So in this case, none of the charge carriers is not paired with any electrons, and under this unbiased, the conduction is represented as 0. Then we'll see what happens when we are applying the biasing with respect to the tunnel diode. So let us consider if a small voltage in a forward bias condition. First, I consider a small voltage is applied to the tunnel diode. A small voltage is applied to the tunnel diode. And based on the normal PN junction diode principle, whenever the PN diode is biased with a forward bias, what happens? The depletion width is decreases, hence it allows the diffusing of the charge carriers. Means if the depletion width is decreases, means the potential barrier height is also decreases. Means the space charge region is also that is a reason. Whenever the charge particle, whenever your applied force is to the charge carrier, that should be higher than the space charge region voltage, hence it diffuses the charge carriers from the one region to the another region. So let us consider this is a potential barrier, and and previously this is the height of the potential barrier, and this is the height of the potential barrier. So for this unbiased diode, now we are going to apply a small forward voltage. So when we are applying the small forward voltage for a PN junction diode or a tunnel diode, the concept is it decreases the depletion width. Hence, the potential barrier height is reduces. So hence, the potential barrier height is reduces. Hence, only the sum of the charge carriers. We are applying only the small voltage. Means the diffusing of the charge carriers or the concentration rate is directly proportional to your applied electric field. And here we applied a very small amount of energy, hence a small amount of charge carriers or diffusing from the means. Due to this, what happens here? This is the height. So previously, so these are the space. This is the energy is required. This amount of distance is there to travel from the one region to the another region. Now, what we are doing? We are applying a small means we are decreasing to share the charge carrier from the one region to another region to be we are going to reduce. Hence, so here only small amount of the charge particles are diffusing from the N type to the P type, hence to allow the conduct. So hence, when a voltage is a sum V, the input voltage is small, hence the conduction rate is also very small here. And similarly, for this case, so that is the reason some points we observe when a small voltage is applied to the tunnel diode, which is less than the built-in voltage of the depletion layer. So no forward flows to the junction. However, a small number of electrons in the conduction band of the N region will tunnel to the empty states of the valency band. So this is the tunnel means this is, but we are applying a very small voltage. But what we discussed the tunneling effect. So what is the meaning of tunneling effect? Even though if the charge potential energy of the electron is a very less or very less compared with the space or region, due to the thin region of the tunnel diode, that less energy of the charge carrier is also trying to diffuse from the N-type region to the P-type region. This mechanism is called as the tunneling mechanism. So due to the tunneling concept, a very small amount of the charge carriers are diffusing from the N-type to P-type, hence it allows a small current. So that is the same point I represented here. Then I am going to increase your applied voltage is again further increases. So if the voltage, forward voltage is going to be increases means the potential barrier height going to be reduces. Height is going to be reduces. So under this condition, what happens? So means having the more number of free valency holes, and we have the conduction charge carriers, hence more amount of force is increases means the diffusing of the charge carrier concentration rate is also increases. Hence the conduction rate is also increases. So that is the reason I'll show this one. What happens when applied voltage is slightly increases. So under this condition, a large number of free electrons at N side and the holes at the P side are generated. Because of this increase in the voltage, the overlapping the conduction band and the valency band is increases. Then suppose again you are going to be increase a further voltage. So what happens? You goes on increasing this one. So let us suppose in the previous case, if you are having this one, so goes on increasing this one. What happens at particular point? These two regions are becomes equal. Means so they having this is a real space. So it having some tunneling. So means the maximum number of the charge carriers are diffusing from the N region to the P region. That I shown here. So in this case, up to this point, this is the VP, means up to this peak voltage, the tunnel current is increased. Now what happens after whenever it reaching to the peak voltage? Even though if you are applying the voltage, another forward voltage, so what happens again is going to be potential barrier is going to be reduce. So hence at this point what happens here, and this is the charge carriers, but here there is no empty space and they are already filled with a valency band. Hence none of the charge carriers are there in a p type so freely. Hence none of the charge carrier is not attracting towards the holes. Hence the conduction rate is going to be decreases from that point. So if the applied voltage is further increases, so that is the reason, and that is the voltage is going to be reduced. So under this point, again, this is called as a valley voltage. At this point, this is called as a peak voltage. Means at which voltage, then again the conduction is going to be reduced. Under this point, so if you observe from this peak voltage to the valley voltage, and here we are applying the voltage is in a forward direction, means voltage is in an increased direction, and this is the current. So under this condition, what happens? The tunneling current is decreases here. The tunneling current is decreases. From the rich region, from the peak voltage to the valley voltage, even though you are applying the forward voltage under the increased direction, the current is decreases. Under this condition, this tunneling diode is satisfies the negative resistance region characteristics. That is the reason. In the initially we discovered that the tunnel diode or Isaki diode is a negative, means the thin junction negative resistance device. So at this point, from the VP region to the VV region, the tunnel diode satisfies the negative region characteristic. So it goes on increasing again, it satisfies the breakdown, means the breakdown is occurs, hence there is no allowing of the controlling of the movement of the charge carriers, hence the conduction rate is again increases. So that is the characteristics of VI characteristics of the tunnel diode. And this one is shows, I'm showing that the symbol of the tunnel diode, and we have the P side material, and this is the N side. And this P side, it is represented as anode, and this is represented as cathode. And this is the shows the tunneling effect. And these are the VI characteristics what we observed from the with respect to the biasing conditions here. So, and up to this point is the peak voltage. It goes on increasing the forward voltage. The conduction rate is also increases. Whenever it reaches the peak point, even though if you are applying the voltage, then conduction rate is decreases up to the with some voltage that is called as the VT. And these are some advantages of the tunnel diode. This tunnel diode have the low noise, and it is high speed, means it requires a very less amount of the voltage to allow the conduction, means that is the reason the speed of the operation is very high compared with the normal PN junction. That means very span of the time period it enters into the conducting state. So that is the reason its device is called as a high speed and low power. So up to this point in this today's session, we covered that what is the tunnel diode and what is the construction of the tunnel diode and we also observed that the characteristics of the tunnel diode with the energy band diagrams. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.